So I'm in the hand for different implementations of Grover's algorithm. The first and obvious one is the one that I can find within the tool from Craig, so Quirk's tool. If you, when you load the tool, you basically have, let me take a look at it. I'm still on the train, by the way, so it might sound, you might hear some background noise. So when you load the tool, you basically have a bunch of example circuits, and the first one is Grover Search. What I want to basically go through with you guys now is basically what are different implementations that I can find, right? And then we'll take this step by step. So the first one is try to get like a sort of a view on the different things and what different implementations and what comes up as weird about them, and then we'll just follow up with other videos and other sessions where I'll kind of deep dive in each of those. The special thing about this one is that it's a bit of a different thing, right? So the oracle is what you would expect. So it's basically, if you take a look at the information that appears here when you hover over the gate is basically the control set pattern that flags that particular combination of zeros and ones with a minus, so with a negative face, right? So it's like a control whatever is that. That's the oracle. Nevertheless, what's interesting here is that the initial part, it basically starts with all the qubits and 1, so just zeros, and then applies the X gate, and then follows the Hadamard. So the actual superposition you start with is basically a different one than what you would usually, or the one I originally found in my first video. So that's the first thing that kind of caught my attention. The actual amplitude amplification, it's an interesting thing as well. But this has an explanation. If you take a look at I think it's algorithmic assertions, and I think the post was about controlled thinking of operations as controls. I think that's exactly. So this is the blog post you want to go through, and I'll probably have to do again because I think I roughly remember what was this about. It's about so Craig is proposing a notation to basically simplify that concept of surrounding operations with Hadamards, because what is essentially happening here is basically, I hope that's not too loud in the background right now. Just pause for a second. You won't notice though. Anyway, let's see. But that's one basically. So it's a bit of a different notation, but what we're doing is basically Hadamards, control Z and Hadamards. And so what Craig is basically translating that into that operation, which is not, I haven't seen it anywhere else, but it seems pretty. It's an x-axis control, and by in and of itself, it just basically means that, or by itself, it just means that conditions on a qubit being on minus off, and this is on and this is on plus off. So it controls on superposition. So on this qubit being on a plus or a minus state, right? So this would be being on a minus state, and this is being into a plus state. Yeah. So basically that's it. So, but that's not entirely sure why this works this way, but because I remember the video. Anyway, I shouldn't really dive into this. Let's go back to the goal of the session now, is to basically find other implementations of Grover's algorithm. I wanted to take a look at the IBM Q experience because I haven't been there for a while. Think quantum computing. I think that here, because I basically want to take a look at what's the implementation there, see if it has changed anyhow from what I had. So that's the thing still remembers me. Let's see. Let me just give me a second. If I log in with Google, or did I log in with LinkedIn or with Twitter? I don't remember. But it definitely has changed. Let me just log in for a second. Okay, so I'm in right now. There's definitely a lot of tabs in here that it seems like it remembers. Okay, so some refresh in terms of annotation. Let me close that up. Close anyway, because I had a lot of. I see it still remembers a lot. Not found. A lot of stuff here that I don't know. Introduction to gates. Okay, so maybe let me take a look at the documentation. Maybe there is quantum computing with IBM-Q, introduction to quantum algorithms with Qiskit. See if I can find. Oh, there is Grover's algorithm. Has there anything changed here? The quantum Fourier transform is here. These were here before, yeah, and Grover's algorithm as well. But this stuff, this is still coming soon. Okay, so this is because I remember this part was not in there. Holistic simulations, transpiling quantum circuits. That stuff was not there. By then, it's still not there. Grover's algorithm. I think this hasn't changed really. Absolute amplification, it's the same. So the geometric explanation is the one they give, and then the Qiskit implementation. Okay, but what's the circuit they implement? I think it's still the same. Yeah. Yeah. Right. Yeah, it's just messed up notation-wise. Yeah, it's still the same. There's nothing changed. So that's the one. That's the. I mean, yeah, the flagging part is different here, but that's basically the one. Yeah, this is a bunch of X. It's a bunch of Hadamard's. Hadamard's in here. They all should belong to the same column, and then you've got like the layer of X. Then you've got like that's the control Z. I still don't get it why they don't use the control Z. I mean, maybe it's because it doesn't come natively with Qiskit, I guess. I don't know. And then you've got, yeah, you see that's kind of awkward because of how the measurements are organized, and then you've got because it seems like they pack. I don't know. That's an awkward way of visually packing these operations. It seems like they pack them as part of the measurement, as if this would be like a change of base. I don't know, but of computational basis. But it's like, I mean, that's definitely you're missing. Like the Hadamard is here, and then you've got a layer of X, next layer, and then you've got another Hadamard layer, and then a measurement. So it's exactly the one that I have in my video, in the previous video. Good. So those are two. So we got 1, 2. What else? I mean, that goes with this one. So, Grover search example. I don't know. I'm just googling. So, Grover's algorithm circuit. What about? I said continuous variable quantum computing. Grover algorithm. Is there? That should be an interesting thing to find. Continuous variable quantum computation of Oracle. Let's take a look at this. Let's take a look at this. Quantum searching with continuous variables. Yay! That sounds like it should be what I'm looking for. It's on ResearchGate. Is the article available? PDF available. Source archive. So it should be in archive. Okay, so I'll download full text. Come on. Oh, it actually downloaded. Okay. Yeah, but that's not nice. Okay, that's it. From what year this is? This is from 2008. That's 11 years ago. First, a fast quantum search algorithm for continuous variable is presented. The result is the quantum continuous variable analog of Grover's algorithm originally proposed for qubits. A continuous variable analog of the Hadamard. A continuous analog variable of the Hadamard. Yeah, the Fourier transform operation is used in conjunction with inversions about the average of quantum states to allow the approximate identification of an unknown quantum state in a way that gives a square root speed up over search algorithms using classical continuous variables. Also, we know that this quantum search algorithm is robust for a generalized Fourier transform on continuous variables. There's something, I should probably take note of this, because there's also something with Fourier transforms and Hadamard being actually a small version of it, or a Fourier transform. And then this having to do with the something with interference and the waves. But this is another topic. I'll just take note of that. Give me a second. Cool. But that's like 11 years ago. Maybe there's something more recent, something that I can implement. Maybe with Xanadu's Strawberry Fields or Penny Lane. I'm bad at the product naming. The Road to Quantum Computational Supremacy. Okay, that must just have. That doesn't look like the good thing. Continuous error quantum computation of Oracle decision problems. 2012. The problem of searching a database is an example of what is termed an unstructured problem. The classical view of the problem of searching an unstructured database is Grover's algorithm. Grover's algorithm has been shown to. Okay, yeah, but it's nothing here. It appears 5 times. The same speed observed using Grover's. Okay, there are 2 examples of continuous. Okay, there are 2 examples of continuous variable quantum algorithms in the literature. The first is the quantum search algorithms 48. This algorithm demonstrates. It's from 2001, that's even older. But I maybe could take a look at it. Definitely. Does this even open? Does this even open, people? I'll just search that. Good. There was, though, another. This algorithm demonstrates that same speed up using. Okay. But this. The fast quantum mechanic algorithm for database search. Okay, that's the original one from 1996. Okay, so this is the. This is actually from year 2000 PDF. I probably should save this. So we've got this. It's in the paper here. Quantum searching with continuous variables. We could take a look at it. Good. I might ask. I might ask Twitter as well. That's probably one of the other things that I will do. Is I'll just quickly tweet about it. So maybe. Hey, quantum computing researchers. Can anyone, or does anyone know of any CVQC algorithm for quantum, or does anyone know of any other Grover's algorithm implemented for continuous variables, or how I don't even know how to write that question. Such as, does anyone know of any other Grover's algorithm? Any other any other? So this is CVQC. Oh, come on, CVQC version of Grover's algorithm. I found the following papers from 2000, from 10 plus years ago, and I was wondering whether there's something, there's been some recent publications. some other recent publications as well. Or projects. So this is the one. And this is the other condensation continuous variables. Come on, I'm over the limit. I'm gonna say I don't know. There's no cross algorithm. Of any other cross algorithm. Okay, let's see what happens. Oh, sorry, I forgot to tag, because I know, I'm quite sure that this appearing somewhere in appearing. I still recall this appearing in some of your QML slides. Could it be? Could it be? Cool. Let's see. What have we got so far then? So we've got so far this. This is another one. Okay, I'll save those links for later. Okay, so let's go back to search. Is there a real life example, Grover's algorithm, code example, Grover's algorithm? Let's take a look at this. Is that different anyhow? How does it work? Boom, 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 boom. Oracle operator for binary. Okay, so this is just the flagging operator. Grover. That's the same. That's the same like IBM's implementation. I see. Yeah, that's the same. It's pretty nice. It seems to be a nice explanation though, but it's the same. But you see, it all starts with a positive superposition, while Craig starts with a negative one. But then I guess that then has to do with the usage of these operators. Or not, really. That's the funny thing, right? Because if you unfold these, this is just a bunch of Hadamarts and a controls and a control. I don't know. It seems to be the same like these. I don't know, but without these X's actually. That could be, that's interesting. Maybe that's why he starts with these. Just to spare these not layers. Okay, but that's the same. So I'm gonna ignore that. Let's keep searching. What else isn't here? Grover search algorithm. Let me quickly scan that due to video. Maybe there's something in there. Maybe there's something in here in terms of a circuit. No. Okay, so here there's a circuit. Let me see. Yeah, it's for 2 qubits. I don't know if you can see me zooming in though. An S gate? Okay, sorry. That's the flagging part, but it's the same like IBM's. Okay, that's the same like IBM's. Same one. The complete 3 qubit research on a programmable quantum computer. That's from Nature though, so I might have to. I hope it's not behind a paywall. Of course, no. Okay. Oracle amplification. Okay, it's the same. Yeah, this is the same. Okay, same implementation. That's a different thing though. What are those things here? XX gates data. Rotations. What is this? What is this? Oracles were constructed using a combination of reversible and classical logic synthesis techniques. For Boolean oracles, reversible logic synthesis. What is these though? Programmable quantum computer. There's a bunch of rotations and B Grover amplification stage implementation. What the heck is that? That might be worth taking a look, but it's like, what's the? Is this paper somewhere else? Is it? Can I download the PDF version? That's from 2017, so that's interesting. Okay, so here's the PDF. I hope I don't have to pay for that. No. Complete 3 Grover search on a programmable quantum computer. I can definitely take a look at these. Okay, this seems interesting. Single solution oracles. There's a bunch of oracle collections in here, and it's interesting. 2 solution oracles. And then there's a bunch of, I don't know, were they trying to do that with a different set of gates, or what is this? I don't know. Okay, cool, I'll take a look at this. That seems to be also a different version. What else? What else? Instructional quantum algorithms. Grover search algorithm from David. Oh, let's see, David. David, you have a. I didn't know you had an article about it. Okay, but I think it doesn't go through any circuit. It basically goes through the. Mathematical. Okay, so just taking the measurement. Okay. Grove's search algorithm is Grover's search algorithm. It might be worth taking a look at as well. In Python and the Rigetti Forest platform. Okay, but it's basically he's not doing it in a CVE in a continuous variable way, right? Inversion about the mean. Okay, so he might be taking a different view on this. I'm gonna keep it as well. We got a bunch already. So 1, 2, 3, 4, 5, 6, and Grover algorithm. What is this? I'm going to page 3 in Google. That's not common. Quanticky. Let's take a look at Quanticky. Maybe let's take a look at circuits. Maybe there's something else. Oh, yeah, that's like a. That's like an old version of the implementation of Grover's algorithm with an oracle of n equals 3 searching for 101. But I think this is an old implementation from the IBM Q experience as well. But I might take a look at it. Maybe this is somehow enlightening. Okay. So here, wait a second. August 3rd. Where is that from? Diffusion, eval, diffusion. Yeah, but that's basically... Or these. Grover's Quantum Search Algorithm, Twisted Oak Studios. That's where can I find that? Can I just click in here and find it? Or does it go directly to the place where the image is? Oh, it's posted by Craig. Okay. I'm definitely gonna go through that. If I don't know if I hadn't actually. Maybe I did already, but it's this is really Craig actually. That's pretty cool. Oh, there's actually stuff with beam splitting and stuff like that. Hmm. Okay, I mean it's a different take on that, but it's not. It doesn't have to be a different algorithm here. Okay, still 10 minutes. So it seems like I've gotten replies already on Twitter. Nice. Yeah, the CVQA paper, we show a special case of CVQA searching for a small ball in a nine-dimensional space instead of being like CV Grover. We cite this paper, I believe. Cool. Then I'll take a look at it, definitely. The CVQA paper. From this I have the link, so I'll keep it. Okay, cool. That's nice. Thanks. Cool. Thanks, yeah. Okay, perfect. Grover search algorithm. It seems to be the same. Bum bum bum. Oh, there's not even a circuit in here. Okay, but I think it's kind of. I think there's no really nothing here. Nothing super different than again the same geometric explanation. Okay, it's the same. So I don't think there's any other. Basically, we've got two main differences. So we've got, and that's, I mean, that's really definitely the original one, right? So the step preparation, the oracle, and the Grover operator. So this is it. It's just the Craig has a bit of a slight different implementation, using these different gate controls. And then I want to take a look at the quantum, at the continuous variable one, to try to see if I can, if this kind of brings a bit more extra intuition to the whole mix. And then this David stuff, yeah, I think we've got quite some work to do. I don't know exactly why this is this way, but there's a bunch of control nodes and T gates. But I'm assuming this had to do with some early limitations on IBM's computer. We'll see. We'll see. Cool. Perfect.